So in this lecture, I'm going to discuss about full adder circuit. Oh, now the first thing is when we have to use the full adder, that you need to understand. Suppose, so in order to understand full adder, few things you need to understand. So I'll start each of the thing and I'll come to this full adder idea when you have to use the full adder. For example, if you have gone through my last lecture, which is based on half adder circuit. So what I told in that lecture, if you have given two numbers and each of the number is having single bit, then you can use half adder to add these two numbers. Okay, so if one has to be added with one, you know the result is some result is 0 with k equal to 1. Okay, that is possible in case of half adder. Now the problem is if three numbers are given and each of the number is having single bit, is it possible to do the addition using half adder? No, because in half adder you have only two inputs, A and B. So if you have given three numbers, suppose 1, 0, 1, and if it is asked to add three numbers, okay, which circuit can be used to add these three numbers? Definitely in digital electronics, a circuit is there which is known as full adder, which can be used to add three numbers where each of the number is having single bit. And this is the generalized idea. Now, if we want to go to more depth, okay, then what is the idea actually? The idea is, suppose you have given two numbers and each of the number is having two bits. For example, you have number A, you have number B, and each of the number is having two bits. So suppose I'm representing it by A1, A0 and B1, B0. Okay, suppose these numbers are first number is 0, 1. The second number is also 0, 1. Okay, and these two numbers, suppose you need to add. Okay, this is representing MSB, this is LSB, and this is MSB, this is LSB of the second number. This for the first number, this for the second number, and these are the numbers. Okay. Now, if this task is given to you where you need to add these two numbers, what procedure you are following? One, you are adding with one, the result becomes 0, and some carry is there that you are propagating to the next stage, and you are adding this one with these two numbers. So 1 plus 0 plus 0, so the result is 1. Now the thing is that this right side portion, as you have two bits, that you can use a half adder circuit to add these two numbers. However, if you see this left side portion where three bits are there, means three numbers are there and each of the number is having single bit. Is it possible to add by using half adder? No, you have to use full adder circuit. So how you can clearly tell regarding this particular thing? What you are doing actually, you are adding two numbers with a carry digit. Is it yes or no? Yes, we are adding two numbers having single bit with a carry digit. Okay, and this is the idea of full adder where two numbers you need to add where each of the number is having single bit with a carry bit. So you can consider this your carry bit and this is your one of the number. You can consider this A and this number you can consider as B. A is single bit, B is single bit with the carry result. Okay, so these three things you need to add and each of the number is having single bit. So this is the idea of full adder. If you are given such type of problem, then you have to use full adder circuit to implement this thing. Okay. Now, how to do? So if you have given three numbers and each of the number is having single bit, so you can write first truth table. A, B, C, and this as I'm considering is a carry, so I can write a C in. Okay, so these are the three bits. Okay, so as you have 3 bits, how many combinations are possible? You have 3 combinations because carry in this particular problem, carry is coming 1, but it is not mandatory that for every problem, this carry bit will come 1. It can be 0 also. Okay, so we can consider these 3 bits and means using 3 bits, we need to find different combinations. So if you have 3 bits, how many combinations are possible? 8 combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now let me tell you, similar to your half adder, your full adder circuit is also having 2 outputs. Okay, let me give the brief idea of that thing. So if you want to give the block diagram representation of full adder, so you will have 3 inputs, means A and B are the main inputs. Each of the input is having single bit with your carry input. C is also will be a single bit because carry definitely it will be a single number, a single digit. Okay, and you will have 2 outputs. One is carry out and other one is sum result. Okay, 2 outputs will be there. So this is the block diagram representation of full adder. So you have these inputs, 3 inputs, and you have 2 outputs. What are the outputs? One is sum, other one is carry out in case of full adder. So based on these 3 bits, we need to decide what should be sum and carry value. Okay. So if you add 0 with this 0, then what should be the sum? Sum is 0, carry is also 0. If you add these 3 numbers 0, 0, 1, if you add what should be the sum result? 1, carry is 0. So sum is 0, carry is 1. If you add this 0 with this 1 with this 0, what should be the result? This is well known to everyone. Yeah, I made a mistake here. Here sum is, as I written here, sum is 1, carry is 0. So 0, 1, 0 here it should be sum is 1, carry is 0. Then you have 0, 1, 1, and suppose 0, 1, 1 is given to you. If you add these two numbers, one result, sum result is 0 with carry 1. Okay, so sum result is 0 with carry 1. Okay, so likewise you can do for all these numbers. So 1, 0, 0 means sum is 1, carry is 0. 1, 0, 1 means sum is 0, carry is 1. 1, 1, 0 means sum is 0, carry is 1. 1, 1, 1 means sum is 1, carry is 1. Okay, so this is the truth table of full adder. Now, how to get the expression? As you know, if you want to get the simplified expression from for sum and carry, we need to use this thing. We need to use K-map. So use K-map to find out the simplified expression of sum and carry. It will be definitely 3 variable K-map as you have 3 inputs A, B, and C. Fine. So 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So put these values. Suppose we are finding out first for sum 0, 1, 1, 0, then 1, 0, 0, 1. Okay, is there any combination or pair possible? Not at all. So what should be the expression? We need to write individual components. So let me write down the individual components. Suppose we are starting from here. So it is A, B bar, C bar, and for this one, it should be A bar, B bar, C in. Okay, plus for this one should be A, B, C in. For this component, it should be A, B, C in bar. Okay, so from here, what we can do, if we take, can use different color also. If I take this B bar common, this B bar and this B bar. So if I take B bar common, then I'll get A C in bar plus A bar C in. And this is a well-known expression to everyone. And from this part, what we can do, we can take common B. So from if you take common B, then A C in plus A C in bar. This is also a well-known expression. Okay. So if I take common, B bar, AC bar, B bar C, and from here AC, and here I think it should be A bar, not A. It should be A bar. Because this component means from left side is coming A bar, BC bar, yeah. So this should be bar. Now, after that, what you can do? This is the expression of XOR gate. So this is nothing but A XOR C in, and this is also a well-known expression AC plus A bar C in bar. So what does it mean? This is the expression of X NOR. So we can write as A XOR C in whole bar. Okay, this is the expression of X NOR. After that, if you see this expression closely, so you can think of this is one variable as X bar. This you can consider as Y. That you can consider as X. This you can consider as Y bar. Try to understand what I'm saying. So suppose let B equal to X and A XOR C equal to Y. Okay, then what we are getting from here? X bar Y plus X Y bar. So this is also a well-known expression for everyone. Is X XOR Y. So now replace the value of X and Y. So X as we have considered B. So replace these values. So B XOR Y is A XOR C. So we can write in this order also A XOR B XOR C. Okay, so this is the expression for sum. Now, same thing you can do for carry also. Find out the expression for carry out. So again, you need to make three variable KML. You have A, B, C in 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, and C out you need to find. So what was the values of C out? Is 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we have 0, 1, 1, 0. No. 0, 1, 1, 1. Okay. 0, 1, 1. Yeah, correct. Now, so from here, what you can do is if we individually means do the pair, then what we'll get? So here you can make some pair. So from this side it is A, and from top it is C in. If you make this combination, then from the left side it is A, from the top it is B, and if you make this combination, then it is B, C in. Okay, so it means A, B, B, C in, then C in A. Okay, now we can write in a different form also, and I will tell you why without using this expression generally why other expression is generally used in most of the book. I'll tell you what is the reason. So the other way we can find the expression is suppose this is the component, write down this component, individual component. It is A, B bar, C in plus for this one. A, B, C in for this one. A bar, B, C in for this component. A, B, C in bar. Okay, now from here, what we can do, we can take common as C in. So suppose if we take C in common, then what we'll get? Suppose from this one and this one, not from this one, A B bar and A bar B. These two components we can consider. Okay, so if you take C common, then it is A B bar plus A bar B, and this is a well-known expression. And rest of the components are, so from the rest of the components also, is it possible to take something common? Yeah, AB we can take common. Then rest is, for example, these and these components are there. So if I take AB common, then Cn bar left. Then what should be the expression? So Cin A XOR B plus AB, and you know, if you add these two components, that you are having the result of 1. That has to be multiplied with AB. So ultimately the result is Cin into A XOR B plus AB. Right? So generally you will see in the book this expression is written. Okay. Why? Because if you use this expression, here one component is there A XOR B. Okay. So when you will implement this thing, means you will means when I will show the internal circuit of this full adder, you will see this expression has been used. Okay. That's why people generally, or in many of the books, you will see this expression is given. Okay, because this expression you will find here, as well as this expression is coming in this sum result also. So same expression can be used for sum as well as carry also. So in order to that, means as we are getting this expression in both the cases, so that's why this expression is generally used without taking this expression. Okay, because this A XOR B is coming in the carry result, C out result, as well as sum result also. In the sum result also. Okay. Now, how to make the circuit? So you have three inputs, A, B, and C. Now, another thing I will tell you, why in most of the books or most of the documents you have found out that this type of circuit is given, whereas because you see some expression is given as A XOR B XOR C in. So we could have used a single XOR gate where three inputs are there. One of the input is A, B, and C in. But without taking this one, actually in most of the cases you will see this type of circuit is given. Now the question is why? The answer is because in hardware, if you want to implement this thing in hardware, you will see whatever the XOR gate we are using in most of the case in laboratories, that is 7486. This is the number of IC number of XOR gate. Okay, this is having two inputs. So three inputs are not possible for this XOR gate for 7486. Okay, so it is having two inputs only. So as it is having two inputs, so at a time you can give only two inputs. So three inputs are not possible in a single XOR gate for this particular IC. And you will see in most of the labs these IC is available. Okay, so that's why without giving three inputs in a single IC, two different XOR gate, without giving these three input in a single XOR gate, two different XOR gates are selected in the circuit. Okay, this is the reason only. Now we can do the remaining part. So this, this the expression means 1C also we need to give here. So it becomes sum. Okay, this is a sum result. A XOR B XOR C in. And what about carry? So if you can remember what was the expression of carry. So A XOR B, this result we can take from here. So that's why I told why this expression is used more. Because here, whatever output you got for the sum result, here you got some intermediate output that can be utilized to get the overall carry out also. So that's why this expression is mostly used. Okay. So this intermediate thing is also required. That has to be AND with C in. So as you have this C in, we'll make AND with C in, this one C in, and this other input. You have this AND gate output. So we have found out this part till now, and we need to have AB. So AB how to get? You have to use another AND gate to get this AB. One line you take from here, one line you take from here. Use one AND gate. So this is your AB, and finally you need to add these two things by using an OR gate, and this is your carry out. Okay. Okay, so that's why without taking this expression in most of the without taking this expression, this is also correct. Okay, this is also correct. So that's why without taking this expression in most of the case, they are using this one. Okay, because in this expression, this A XOR B is there, and that is one of the intermediate value for the sum result. Okay, and that is directly can be used to get the carry out. Okay, so thank you very much.